My name is Venta Terauds from the University of Tasmania. You may recognise my name from many emails that I seem to have been sending lately. Welcome to my lo-fi digital talk. So I'm just going to talk about irreducible semigroup-based Markov models today. Markov models probably familiar to most people. Group-based models probably familiar to most people, and this is building on some work that was started by Jeremy Sumner and Michael Woodhams a couple of years ago in a 2019 paper called something like semigroup-based Markov models. And this latest work is joint work with that Jeremy and I did with an honours student, Nicholas Bokanek, in the last 12-18 months or so. Okay, so just to establish that we're all talking about the same thing. Markov models, we think of evolution as a continuous time Markov chain. We begin, or we have in mind, a finite set of states that we want to model, n of them. And for those states, we can make a Markov transition probability matrix. So I'm thinking of column sums here being 1. So the ijth entry of my matrix R is going to be the probability that if the state xj is going to evolve into something, it's the probability that it's the other state, the state xi. Okay, so from a discrete Markov transition probability matrix, we can build a rate matrix. This we're going to call rate matrices Q. And as the column sums of my transition matrix are 1, I subtract the identity matrix from one of those, and I get a matrix whose column sums are 0. Of course, we can also begin with a rate matrix, in which case we just say we have non-negative off-diagonal entries and diagonal entries, whatever is required to make the column sum 0. Okay, so far everything's discrete. Once we add in a stochastic component, a Poisson distribution of events in time, then we can create from our rate matrix via a little bit of mathematics, summing of power series, a continuous transition probability matrix. So we end up with a continuous transition probability matrix P, which is time dependent. It's the exponential of the rate matrix multiplied by whatever our time is. And so rather than the probability of something occurring, evolving via one discrete event, this is the probability of one state evolving into another, or gives the probabilities of each state evolving into each other state in a certain amount of time. Okay, Markov matrices. We take a collection of Markov matrices, and that's what we mean by a Markov model. So it's a collection of rate matrices for a fixed set of states. Okay, so as an example of a Markov model, we tend to write them down as a matrix like this, the well-known Felsenstein 81 model, or the equal input model. So in this case, we have four parameters, alpha, beta, gamma, and delta. But I like to write them down, or we like to write them down as sets. So it's the set of all matrices that look like this, where my parameters are non-negative, and the stars are simply whatever we need to make the column sums to be 0. Okay, so Markov models have been widely used in phylogenetics for a very long time and have been widely studied. And obviously, if we want to study something and understand about it, it's useful to be able to classify it in a certain way. So one particular subset of Markov models that are known to have good properties, value judgment here, good properties are the group-based models. And people at UTAS, Jeremy and colleagues, have particularly looked at the property of closure that we have in group-based models. So by closure, what we mean is if we take two matrices from a given model and we make their continuous probability transition matrices. So we've got two different ones of these, maybe, different values of these parameters, but the same shape matrix or from the same model. And we have evolution according to one of these, and then evolution according to the two of these. Well, we combine these two matrices together. Do we get, we certainly get a third matrix, but do we get one that can be expressed, or that comes from a rate matrix from the same model? If we do have this, then this is, we say that the model is closed. So group-based models have this property. Group-based models are nice. Are all nice Markov models nice? Well, no. So this model, for example, is not a group-based model, but it is known to be closed, and it does have various other nice properties. So Jeremy and Michael Woodhams in 2019 noticed or derived that this particular model, amongst others, is an example of a semigroup-based model. So in order to describe what a semigroup-based model is, I'm going to reverse engineer the equal input model. I'm going to go to a three-state model because then I have to do less writing. So let's consider the equal input model on 3 states. And that means I'm going to take a matrix that looks like this. You know, the model is the collection of all of these. I'm just going to take one of them. I've got 3 parameters. Problem with writing in real time, there will always be some typos, and alpha minus beta, even minus alpha minus beta. Okay, so, you know, constant rows apart from the diagonal where I have whatever I need to make the columns 0, the equal input model. So how do we kind of try and deconstruct this model? Well, this matrix, a matrix of this form, we think about maybe taking out our parameters and writing a matrix of this form as alpha, lots of something, plus beta, lots of another matrix, plus gamma, lots of another matrix. And if we do this, I'm not going to fill in all the details, this is obviously quite straightforward. We have a look at it for a while, you know, this is a rate matrix, and we think, well, there's a bit of a pattern there. What if I write this of the, in terms of alpha times a particular matrix minus the identity, plus beta times a particular matrix minus the identity, plus gamma times a particular matrix minus the identity. So sums of rate matrices are rate matrices, right? You add up a bunch of column sum matrices, you're going to get another column sum matrix, column sum 0 matrix. Turns out if we do this, if we take out the parameters in this way, then these guys in here are rate matrices, and these ones in here are actually discrete transition matrices. Well, if you have to scale them, maybe depending on what the values of the parameter were, but you're thinking you're getting something a bit like a discrete transition probability matrix. So in this case, what are the matrices that I get? I get the matrix that had 1s on the first row, and I get the matrix that had 1s in the middle row and 0s everywhere else. And I get the matrix that had just 1s on the bottom row and 0s everywhere else. So what have I done? I've started with a matrix, a rate matrix, and I've now expressed this original matrix as a linear combination of my parameters multiplied by these 3 matrices minus the identity. And these 3 matrices actually have a quite special property. If I just look at the set consisting of these 3 matrices, I'll notice that they form a semigroup. What's a semigroup? It's simply a set that's equipped with an associative binary operation, right? We can just think of the operation as being multiplication. Certainly it is matrix multiplication in this case. Matrix multiplication is associative. If I want to multiply 3 matrices together, A, B, and C, doesn't matter which 2 I multiply together first. If I keep them in the same order, right? I can put the brackets on the first 2 or the second 2. That's all associativity is. So If I take any pair of these matrices and multiply them together, I get another matrix that's in this set. This is a particular type of semigroup. It's called the left zero semigroup. So if I take any two things from my set, I can call them A and B, or M1 and M2, or MI and MJ. But for any semigroup that has this property, it's going to be called the left zero semigroup. If I multiply A by B, I'm always going to get A, right? So in this case, if I multiply M1 by M2, I get M1. M1 by M3, I get M1. M3 by M2, I get M3, and so on. So it's a particular type of semigroup. It's a collection of things. I can multiply them together and get something else in the set. And in particular, if I multiply two things together, I get the one that was on the left. Okay, so a semigroup is a generalization of a group. I've mentioned group-based models. So a group is a semigroup, but also we have an identity element. We have something in our set that if we multiply it by anything, it doesn't change the thing, right? It's like the one, the identity matrix. And groups also have inverses. So for each element in my set, there's something else that I can multiply it by to get back to the identity. And generally, traditionally, people have worked with abelian groups. So things where you multiply things in either order, doesn't matter, you get the same thing. But groups don't need to be abelian. And in particular, semigroups, generally not. This one is clearly not abelian. If I multiply AB, I get A. If I multiply B by A, I get B, right? The opposite order, I get something different. Okay, so I'm saying this is an example of a semigroup-based model because when I did this deconstruction process, I ended up with three matrices that formed a semigroup. So we say, well, does that mean I can just take any semigroup of matrices and combine them, subtract the identity from each one, multiply them by some parameter, add them up, multiply each one by some parameter, add them up, and what I get is going to be a Markov model? No, that's not enough. What we need to have is that our matrices are the representation matrices of a semigroup. So I will briefly, I forgot to look at the time, so I hope I'm not rambling on for too long. I will briefly just go over what the representation of a semigroup is. So basically, given a semigroup, we can completely express the semigroup by saying what its elements are. In this case, my semigroup is going to consist of the elements X, Y, and Z. And to completely specify it, I need to say what the multiplication is. In the case of the left zero semigroup, it's easy. For any AB in my set, AB is A. In the general case, of course, it's not so simple. So I write down something called a Cayley table. So this tells me what happens when I multiply X by X. I get X, XY is Y, XZ is Z, YX is Y, and so on. I express my multiplication, I'll summarize the multiplication in this table. So here is an example of a semigroup. The left regular representation turns my semigroup, turns each element of the semigroup into a matrix. And the way it does this is just by looking at what the multiplication does. So X is going to turn into my matrix M. I'm going to index by X. And I think of labeling the rows and the columns by the elements of my semigroup, X, Y, and Z. And I just look at what happens when I multiply everything in the semigroup by X. So XX is X, so I put a 1 in the X spot. XY is Y, I put a 1 in the Y spot. XZ is Z. This is actually the identity. X acts as a left identity in this semigroup. It doesn't do anything to my elements. And so I get the identity matrix for the representation matrix of my element X. I do the same for my element Y. yx is y, so I put a 1 in the y spot. Yy is y, so I put a 1 in the y spot. And yz is z, so I put a 1 in the z spot. What about z? I want a matrix corresponding to my element z of my semigroup. Well, z turns everything in, well, z multiplied by anything on the left gives us z. So zx is z, I put a 1 in the z spot. Zy is z, I put a 1 in the z spot. And zz is z, so I put a 1 in the z spot in the z column. Okay, I've turned my set of elements into a set of matrices. The point of the left regular representation, or it represents the semigroup, which means if I were to look at matrix multiplication and make a Cayley table for my matrices mx, my, and mz, I would get exactly the Cayley table that I have up here for the elements x, y, and z. So the set of matrices represents the semigroup in the sense that it preserves the operation. Have one thing for each element, and they play together like the elements of the original semigroup play together. Okay, so I deconstructed a model and said it was group-based. Now I'm starting with a semigroup-based. Now I start with a semigroup, and I'm going to build the semigroup-based model from this semigroup. So I've done the first step. I've created the representation matrices. I then look at linear combinations of each of these matrices with the identity matrix subtracted off. Alpha 1 plus beta. Let's just do alpha, beta, and gamma then, why not? My minus I and gamma mz minus I. Okay, and what I'm going to get is going to be something that will look like this. I've changed my own parameters, so that's okay. Let's hope that I can work with that. Alpha 2 and alpha 3 and 0 and 0, 0, 0. Okay, so if I subtract the identity from this one, I obviously get 0. So there are no alphas appearing in my final matrix here. And, you know, subtract the identity from here, multiply it by beta, subtract the identity from here, multiply it by gamma, I end up with this matrix. Now, if I'm going to take the collection of all such matrices, where alpha, beta, and gamma are greater than or equal to 0, I'm certainly going to end up with a Markov model on 3 states. But what I'm not going to get is an irreducible Markov model. I'm wondering if I have already mentioned what irreducible is. I may not have. Sorry if I have. By an irreducible model, we just mean that there is some matrix in the model, and if there's one, there are going to be lots of them, via which every state can reach every other state. So there are no absorbing states or anything like that, but basically everything can always evolve into everything else. And this is the kind of model that we use in biology. We're not tending to use Markov models in which, you know, states get stuck. So we want irreducible ones. We want models such that everything can evolve into everything else. So if I look at this one, well, what happens if I multiply 2 matrices of this form together? These are lower triangular matrices. So I'm always going to have zeros on the top right corner. So nothing is going to be able to evolve into state 1 via this model. State 2 and 3 can evolve into each other, but certainly nothing ends up getting into state 1. So this is not an irreducible model. This model is certainly an irreducible model. If all of my parameters are non-zero, then certainly it's going to, I can, one of these matrices such that all the parameters are non-zero is going to get me, it's going to be irreducible. Everything can get to everything else. Okay, I maybe should write down, I think in general, to make a semigroup-based model, maybe I should write it down. But it's a while since you've been to a Blackboard talk. Semigroup-based model is one of the form, so that S be a semigroup, and let M1 up to N be the representation matrices, the regular representation matrices. Then curly M consisting of I equals 1 up to N, alpha I, Mi minus I, for these non-negative real numbers, alpha I, is the semigroup-based model. Here's a not irreducible one. The other one was irreducible. I promised that we could characterize the irreducible semigroup-based models. So up until this point, this is not new work. This is what Jeremy Sumner and Michael Woodhams did in their 2019 paper. They wrote down basically, you know, how we can define a semigroup-based model, how we can build them, and they found all of the semigroup-based models up to the 4-dimensional ones, up to all of the ones up to a maximum of 4 states. So can we say which ones are, or all of the irreducible ones up to a maximum of 4 states? In general, how to tell if one is irreducible or not? Well, yes, we can, and it's really simple. We kind of can see here that, okay, we can get an intuitive idea here that we don't want to have any zeros. We don't want to have things that are always going to be 0 floating around. And what happens if we add up our representation matrices here? Well, we're definitely going to get some zeros popping up. There are going to be some 1s and some 2s and some 0s. If we look at this equal input model, it's really nice. The representation matrices have just, each representation matrices has a row, matrix has a row of 1s. And if we add up the 3 representation matrices, we end up with the matrix consisting of a 1 in every single entry. Turns out that this itself is a characterization. If I can do this when I add up the representation matrices, I've got an irreducible, or I can build an irreducible semigroup-based Markov model. If I can't, then it's not going to be irreducible. I can build a semigroup-based model, but it won't be irreducible. So M is irreducible if and only if the J matrix, where Jij is 1 for all ij, right? So the matrix consisting of all 1s, nothing else, if and only if the J matrix R is, I've written this backwards, is the sum of the representation matrices. In other words, there is actually a nice simple way to write this. I equals 1 to N, Mi is J. Add up all the representation matrices. Get the matrix that has a 1 in every single spot, no 0s, no 2s, nothing else. Okay, so that's my first condition. That doesn't sound like something that's really lovely and nice and easy to check, but it turns out that this is equivalent to the Cayley table, the multiplication table for my semigroup, having each column being a permutation of the semigroup elements. Right, so all of the elements from S appear in every column exactly once. Turns out that this is equivalent to the semigroup being right cancellative. What does this mean? This means it's a little bit like a group. It means that I take some element of my semigroup and two other different things, and I multiply those two things on the right by my element X, and I get the same thing, then my two elements must have been the same. So for all elements of the semigroup, if Yx is equal to Zx, I must have Y and Z being the same thing. So if you think about the right multiplication map is injective for every single element in the semigroup. Now, hang on, we've said that S is finite. So we're talking about injectivity, then that must be conjectured to surjectivity of the same map. And so there's a kind of surjective equivalent condition that basically if I take any two elements, I can get to one of them by multiplying something else on the right by the other one. Oh, I better write that down. That's called left transitivity. Well, for each X and Y, there exists Z such that X equals Y. Okay, it's a surjectivity thing. So, okay, even so, are all of these things kind of nice and easy to check? I mean, you can, if you want to start to list semigroups, there tend to be quite a lot of them. Well, there are a lot of them, certainly more than groups, right? Because it's generalization, so we don't have to have inverses or identities or whatever. So there are lots of semigroups. So do we really want to list them all and go through them and check, oh, is this one left transitive? I don't know, is that easy to check? Shall we check it, what happens in the Cayley table? No, so these are not nice things to check. But it turns out if you do a little bit of reading about semigroups, if you're not very clever, you first of all prove this yourself, and then you do some reading and you find out that actually it's a well-known property of semigroups. All of these things are equivalent to, or are called, the semigroup is a left group. And there's a really lovely characterization of left groups. It's very nice and simple, and it's related to the left zero semigroups that we mentioned that give you the equal input models. So all of these are true if the semigroup is something called a left group. And a left group is one that we can write as the direct product of a group and a left zero semigroup. Okay. So first of all, it's really easy to check. There are not that many groups, you know, small orders. They're at least easy to, you know, they're well known and well studied. So if we want to produce a semigroup based model, we pick an order, take a left zero. First of all the left zero semigroups give us one and it gives us the equal input model, or we just take the cross product of a left group with a group. So this is a really nice way of generating examples of semigroup based models, and any time that we have a semigroup based model might be one of these. We've obviously got quite a bit still to study. We're in the, you know, beginnings of looking at these, but certainly we're now able to easily generate examples of these and study them further. So when we were first looking at this, I thought, oh, I'll just have a look and see how many there are of each order. So once this is like the order, right? So how many states in this second column, and then we're counting how many left groups, how many irreducible semigroup based Markov models there could be for each order. So if you have a prime, it's quite cool. If your order is prime, well, maybe we're not interested in prime numbers of states, but if your order is prime, then there are only going to be two, because there's just going to be the abelian group with that many elements and the left group, right? Because you can't split up, right? The order of this guy is the order of G multiplied by Q. And so obviously if it's prime, you've only got one of them is trivial or the other one is trivial. Anyway, thanks for listening. And maybe if you've looked at this and you have some questions, then I might see you in the discussion session. No doubt I will see you in the conference in a few days' time. Thanks.